In our most recent further maths video, we looked at how to find the invariant points of a matrix transformation, and therefore today, surprise surprise, we're finding invariant lines of a matrix transformation, because it's worth pointing out invariant points has a more restrictive definition than that of invariant lines. And in fact, that's a good starting point. We should explain what invariant line actually is, and in order to do that, I'm going to compare and contrast the idea of this to what an invariant point was. So a reminder, if you're trying to find an invariant point is a point, unsurprisingly, that if you're trying to transform using a matrix transformation, won't change position at all after it's been transformed. Whereas the points on an invariant line actually can change position after they've been transformed, it's just that they must move to somewhere else on that same invariant line. So that's what an invariant line is. How do we find it? Well, we're just going to launch straight into an example because the steps for finding an invariant line are much easier to just demonstrate than they are to explain and list. So in our example, we're trying to find the invariant lines for the transformation defined by the matrix 3, 1, minus 15, 11. So before we launch into it fully, it's worth pointing out that these questions are quite heavy on the algebra, but don't worry, you are given a fair number of marks to compensate for that, and also I am going to be showing you some important tips and tricks along the way, so do watch out when I talk about those. If we're trying to find an invariant line, what we're trying to therefore find is the equation of that invariant line. So if we're going to assume it's a straight line of the form y equals mx plus c, what we're basically aiming to do is find the values of the m and the c. Therefore, what we're going to say is we're going to start off with a point that lies on that invariant line. Let's call it the point with x coordinate of x, and therefore the y coordinate, if it's going to lie on that straight line, must be mx plus c. If it's anything different from that y coordinate, then it's not a coordinate on our straight line, our invariant line to be more precise. But if this is going to be an invariant line, then this point we've got that lies on the line after it's transformed must still lie somewhere on that line. It might have moved, so it could have a new different x coordinate, let's call it an x coordinate of a, but it's still going to satisfy the equation of the invariant line, so therefore its new y coordinate would be ma plus c. Using this, we can then therefore set up a matrix equation, because we know that 3, 1, minus 15, 11 times by our point that lies on our mystery invariant line must be transformed and then end up still being a point on that invariant line, just a different point, so we could use that second point on the invariant line we'd already defined. All we've got to do now is therefore multiply these things out to create some simultaneous equations. We end up with 3x plus one lot of mx plus c, so I'm just going to write mx plus c straight away, and that's got to equal a. And similarly, we also know that minus 15 times by x plus 11 lots of mx plus c has got to equal ma plus c. And these are going to be some simultaneous equations. I'm going to eliminate the a because it's a ready-made nice substitution that I can just plug into the other thing. So therefore we're going to get minus 15x. I could start multiplying out some of those brackets as well, so I'd end up with 11 lots of mx plus 11 lots of c, but then instead of writing ma plus c, it's now going to be m lots of what a is equal to, which is apparently 3x plus mx plus c. And then we still have that plus c from over there. Cool, now we could start by multiplying out those brackets as well. So I'm going to do that. So that's 3mx and m squared x and mc, and then still that plus c on the end. And then I'm going to rearrange it to make sure that everything is on the same side of the equation as each other. I'm going to move everything to the right hand side just because there's an m squared x on the right. That looks like the most complicated thing, and it's currently a positive version of that thing, so I don't want to make it negative. So let's keep it on the right. So therefore I've got an m squared x. Something you might notice I do with these questions is because there's a lot of algebra about, so I can keep track of what I have or haven't dealt with, then start to do things like I'm doing here, where I'm doing little ticks below or above things, just to say that I know I've dealt with that already. Make sure you don't cross stuff out. That's bad practice for maths for the sake of an exam, because if you cross out your working, the examiner can't read your working, and they might imply that you're saying you don't want the examiner to look at it, but you do because it's your working. So therefore, that's why I'm doing a tick under it rather than crossing it out. Anyway, we also have a 3mx and then a 11mx on the other side, which I'm going to subtract. So 3m take away 11m is minus 8m, lots of x. So I've dealt with those two things. I've got a 15x, so I can move that onto the other side. So that's me now having dealt with all the x's. And then all the things that aren't x's, I still have that mc. But then I've also got a c and then a 11c on the other side that I could subtract to get minus 10c. And so on the left hand side, we're just left with 0. And then moving on to the next slide, so we have more room. You might notice I've done something weird. Okay, yes, I moved what was on the right to the left and vice versa. But more importantly, we've got that triple equal sign, or to give it its official name, the equivalent sign. Now that's for a very good reason, which is that we are trying to find an invariant line, and a line, of course, is made up of an infinite number of points. And all those points must abide by that definition we said earlier if this is going to be an invariant line, which is that any point can move on a variant line, but it's just got to move to somewhere else on that invariant line, which is what led to us setting up this equation in the first place. But the point is, therefore, this equation's got to work for every single value of x that lies on the line. But, therefore, that's why I've written the equivalent sign to make it clear that this should always work no matter what you sub in. But as you can probably see, this isn't currently happening because I've got all these coefficients of m and c. So in reality, this question is changing to us now just trying to find what are the values of m and c that will always make this equivalence be true. In order to make that a bit easier to discover, I'm going to factorize x out of the first three terms. So that will leave me with a quadratic m squared minus 8m plus 15, lots of x, and then we've got the bits that aren't affected by x, or aren't involving x, I should say. So we've got the mc minus 10c equivalent to 0. Now, if we want this equivalence to be true, there's actually only one way it can happen, and that's if we have 0 lots of x plus 0, because that is something that will always be equivalent to 0 no matter what value of x you plug in. To understand the logic of why that is the only case that works, have a think back to equations. If you got the equation 2x plus 1 equals 0, it can equal 0, but only at one specific point, when x equals minus a half. If you plug any other x value other than x equals minus a half into that equation, it won't be true. And that's because if you plug in x, it changes the part that's got an x in, which mucks up the entire equation. So the only way to get around that is if there were no x's at all, because then it isn't affected by what x value you plug in. But then the constant also has to be 0, because otherwise the equation or equivalence would be saying 1 is equivalent to 0, which of course is wrong. And therefore, if we want to engineer that into being true for our equivalence, we know that m squared minus 8m plus 15 must equal 0, and also at the same time, mc minus 10c must also equal 0. Both of those facts have to happen at the same time, and therefore you almost got to view this as an intersection situation. The solutions to the first equation also have to happen at the same time as the solutions to the second equation, so it's the intersection between these solutions that will make the whole thing true that we want to have happen. So therefore, now solving these equations individually, the thing on the left of course is just a quadratic. Luckily it's a super easy one to solve, it's one that factorizes. What a novel idea in further maths. So we get m equals 3 or m equals 5. But then in our second equation we can factorize that, we can factorize the c out of both terms, and therefore we have the solutions either c equals 0 or m equals 10. But what are we going to do with these values to get our final answer, because we're trying to find the equations of the invariant lines? Well, again, reiterating that we're looking at these solutions and seeing where they intersect with these solutions over here. There are a few different ways you could approach this next part, but my favourite tried and tested approach is to choose one of the things from the left hand side and pair it with one of the things from the right hand side and try all the combinations of that process. So therefore I'm going to try picking m equals 3 from the left and pairing it with c equals 0, which was something chosen from the right. Or I could do m equals 3 with m equals 10. Or I could do m equals 5 with c equals 0, or m equals 5 with m equals 10. We're then going to consider each of these combinations in turn, and then think what impact that combination would have on a possible invariant line equation. So let's start off with that first situation, m equals 3 with c equals 0. Well, if you plug that into the equation y equals mx plus c, that's telling you we'd have the equation y equals 3x. And therefore y equals 3x is an invariant line for our particular matrix transformation. For the second combination, things get a bit weird. We've got two different m values, but the problem is in the structure of y equals mx plus c, there's only one place we can plug the m in, and it can't be two values at the same time. So therefore, actually, with this second combination, that leads to no useful information, because it's a contradiction. M can't equal 3 and 10 at the same time. The third combination, we're back to a more regular solution. If m is equal to 5 and c is equal to 0, we're left with the equation y equals 5x in the format y equals mx plus c, and that's therefore a second invariant line. And then for the fourth combination, again, we've got that weird contradiction. M can't equal 5 and 10 at the same time, so that's also no information. So therefore our final answer is we've got two invariant lines, y equals 3x and y equals 5x, and those are our final answers. As I said, there are other ways that are arguably quicker than what I'm doing here by considering each combination, but this is a nice comprehensive way to make sure you're only considering the right things, and also to logically work out why we're ending up with the lines that we do. Hopefully you find that helpful too. However, I haven't told you the full story because there can be some combinations that don't cause a contradiction, but also don't actually specify what the other letter is going to be equal to. For instance, if both of the combinations are talking about the same value of m, then what does that mean c's got to be? Well, the answer is, well, that other letter could be any value you like. And in fact, that means you're left with an infinite collection of lines. Let's take a look at an example so we know what that would look like in the context of a question. As large parts of this example are very similar to what we did before, I'm going to go through those bits very quickly, but do watch out because there are a few little talking points along the way. So, kicking off, we're going to have our matrix transformation multiplied by a point that lies on our theoretical invariant line. Let's say it's x mx plus c, but then if that point's going to lie on invariant line, it can move but just somewhere else on that same line, so I'm calling it a ma plus c, the other point on our line. Multiplying the matrices together to create some simultaneous equations, we end up with minus 4/5 x plus 3/5 lots of mx plus c is equal to a, and then we also have 3/5 x plus 4/5 mx plus c is equal to ma plus c. We can then combine these equations into one, so therefore we're going to end up with 3/5 x plus 4/5 mx, if I start multiplying the brackets out as well, 4/5 c, and on the right we did have ma, but now we're going to have m lots of minus 4/5 x plus 3/5 mx plus 3/5 c, and then not to forget the plus c that was already on the right hand side there as well. And then I could multiply the brackets even more, so I'm going to do that. So the stuff on the left doesn't change. The stuff on the right will now be minus 4/5 mx plus 3/5 m squared x plus 3/5 mc, and then we still have that plus c. Now, because our matrix transformation had fractions in it, that has made our equation look particularly horrible. So of course, the usual trick that you can do is multiply both sides of an equation by whatever is appearing in denominators to eliminate the denominator. So if I multiply both sides by 5, it'll make this equation a lot easier to deal with. So that's me doing that now. However, you do have to be really careful with this, although in most cases it just means we're getting rid of the denominators because they were all the same. We do have to watch out because there was that plus c on the end which didn't have a denominator. So as we are timesing by 5 to eliminate that denominator, everything had to get multiplied by 5, including that c, so it becomes 5c. Then moving everything on to one side of the equation, let's move everything to the right. We've got 3m squared x, we've got a minus 4mx, but then we're taking away another 4mx to get minus 8mx. We've got a 3x that I could move over to the right as well. And then we've got a 3mc, and then 5c minus 4c is just positive c, and therefore that's equal to 0. Again though, this is actually secretly got to be an equivalence, but as before, we are going to want to factorize the x out of the first 3 terms to make it easier to see what the coefficient of x is. We've got the parts that aren't connected to an x, so they're just as they were. But then the only way this is going to be equivalent to 0 for all values of x is if 3m squared minus 8m minus 3 equals 0, and 3mc plus c is also equal to 0 at the same time. Solving both of these, because we're in further maths, we can just use a quadratic formula calculator to help us just work out what those solutions are. So therefore m equals minus 1/3 and m equals positive 3. And then for the other thing, well, we can factorize that, and if we do, we end up with c equals 0 or m equals minus 1/3 again. Which is interesting because now we've got to do what we did before of considering these things in combination with these things. So there's again 4 combinations I need to consider. Let's consider them all. We've got m equals minus 1/3 going with c equals 0. We've got m equals minus 1/3 being combined with m equals minus 1/3. Strange. Then we've got m equals 3 with c equals 0. And then we've lastly got m equals 3 with m equals minus 1/3 chosen from the right. I know there's an m equals minus 1/3 on the left-hand side, but you're only ever picking one thing from the left, one thing from the right, and it just so happens there's another m equals 1/3 on the right as well. So what do these mean for our answers? Well, the first combination leads to the equation minus 1/3 x and then plus 0, so just y equals minus 1/3 x. That is one of our invariant lines. However, the weird stuff happens when we look at the second combination. We get m equals minus 1/3 with m equals minus 1/3. So what do we know from that? Well, we know that m is definitely equal to minus 1/3. I think that's pretty clear. But what's the value of c? Well, what this combination is saying is that there is no restriction on c, and therefore c can be anything. So therefore this combination leads to an infinite collection of lines of the format y equals minus 1/3 plus c, where c is any real number you like it to be. So basically we got a collection of lines that are all parallel to each other but each have a different y-intercept. The third combination leads us to y equals 3x, because m equals 3, c equals 0, and then the last combination had the same situation we had before, where there's no information from that combination because a contradiction is happening. And so what are the final answers? Well, it's actually ultimately just these middle 2 combinations. Although you wouldn't be wrong to include that top combination, it's actually no longer needed because y equals minus 1/3 x is included by the general case of y equals minus 1/3 x plus c, because c can be any real number and 0 is a real number. So therefore these are the invariant lines for our matrix transformation. Cool. So that's how you find invariant lines of matrix transformations. That's the method. It's a bit heavy going on the algebra, but if you consider the combinations, it's not too difficult. But I do have one more thing to tell you, which is that actually there's a little exception to what we were just talking about. Because you must realize that we were assuming all our invariant lines were straight lines of the format y equals mx plus c, which actually isn't always the case. Not all straight lines do have the format y equals mx plus c, because that doesn't include the format we use for vertical straight lines. In other words, x equals 7, x equals 8, those don't have the format y equals mx plus c, there is no y involved at all. So how do you check if your matrix transformation has a vertical invariant line? Well, there's ultimately several different ways you could approach it in terms of trying to prove it, but it rarely comes up ultimately, and therefore most of the time you're just having to know whether you need to bother checking for any invariant lines that are vertical. And the easiest way to do that is just to look at your matrix, and you're basically looking at the top right hand corner element to see if that's a 0. If that number is a 0, then you need to check if there are any vertical invariant lines. If it's not a 0, you know there are no vertical invariant lines, so you needn't bother. Further down the road, I will get around to creating a video showing how you would actually go about proving or finding any vertical invariant lines. Okay, that will do us for today. See you in a future video. That's how you find invariant lines of a matrix transformation.